You type 8 characters into your browser, https://devexops.tech, and press enter. What really happens next? Where do those keystrokes go? How many networks, handshakes, lookups, and security checks fire before a single pixel appears on screen? In the next 12 minutes, we're going to trace the entire journey. Every packet, every protocol, every hop, from your keyboard to the cloud and back. Let's go. Think of your browser as a train station. You've told the station master, I need to get to devexops.tech. Before any train leaves, the station runs a checklist. First, URL parsing. The browser splits the address into 3 pieces: the scheme, HTTPS, the host, devexops.tech, and the path, / meaning the root page. But does it actually need the network? Not always. It checks the local cache. Do we already have this page? It checks the HSTS list. Should we always use HTTPS here? It checks for a service worker that can intercept requests. It checks for an existing connection to reuse. Only when every shortcut fails does the browser say, we need a fresh network request. And that means we first need an IP address. The browser knows the name, devexops.tech, but the internet routes by numbers, not names. So it needs a phonebook lookup. That phonebook is DNS, the domain name system. First shortcut, the recent contacts list. The browser checks its own DNS cache, then the OS cache, then the host file. If any have a fresh entry, we skip the network entirely. But on a first visit, none of those will help. So the OS calls a recursive resolver, your router, or a server like 8.8.8.8. That resolver does the heavy lifting. It asks the root nameservers, who handles .tech. The root says, ask the TLD server. The TLD says, ask the authoritative nameserver. That's Route 53. Route 53 answers with an A record, 76.76.21.21. The resolver caches that answer for the TTL, time to live, say, 300 seconds. Now the browser has an IP, time to build a connection. Your browser calls connect, a system call. Open a socket to this IP on port 443. The OS wraps the data into a TCP segment, then an IP packet, then an Ethernet frame. Each layer adds its own header, like nested envelopes. That frame hits your NIC, network interface card, the hardware that talks to the world. From there, it travels over Wi-Fi, the first local road from your house to your home router. What about VPN users? If a VPN is active, the packet gets encrypted before it reaches Wi-Fi, an extra envelope around everything. The router finds the next hop using ARP and forwards the packet upstream. Your router sends the packet to your ISP, the city road authority connecting you to the broader internet. From there, it enters the backbone, metro fiber, regional links, sometimes undersea cables crossing oceans. But for a site behind a CDN, the packet probably doesn't travel far. A CDN places copies of content at edge locations worldwide. Think of it as a local branch warehouse near the customer. How does the packet know which edge to reach? DNS returned the IP of the nearest edge based on latency or geographic routing. The packet hops through 2 or 3 networks. Your ISP peers with the CDN provider, and within milliseconds, arrives at a CloudFront edge nearby. Round-trip time? Maybe 10 to 30 milliseconds. Before any conversation, both sides agree on the rules. First comes TCP, a 3-step handshake. Your browser sends a SYN, I'd like to talk. The server replies SYN-ACK, I hear you. Your browser confirms with ACK, agreed, connected. That's TCP, reliable, ordered delivery. But HTTPS requires more. Now comes TLS, agreeing on a secret language and verifying identity. Your browser sends a client hello with supported ciphers and SNI, server name indication, saying I'm looking for DevXOps.tech. The server responds with its certificate, a digital ID card signed by a trusted authority. Your browser verifies it against its trust store. They negotiate a shared encryption key. From this point, everything is encrypted. With TLS 1.3, this takes just one round trip. HTTP/2 multiplexes many requests over one connection. HTTP/3 uses QUIC over UDP, even faster. On AWS, CloudFront, or the ALB terminates TLS. They hold the certificate and handle decryption. The browser sends an HTTP GET request through the encrypted tunnel. The request carries headers. Host says DevXOps.tech, plus accept, cookies, and user agent. The first receiver is the CloudFront edge, the nearby warehouse. CloudFront checks, is this content cached? If yes, cache hit. The warehouse already has the item. Response sent immediately. No origin needed. If it's a miss, the warehouse doesn't have it. CloudFront forwards upstream toward the origin. It adds X-forwarded for with the client's IP and X-forwarded proto set to HTTPS. The origin is an application load balancer, the ALB, which terminates TLS on the edge-to-origin connection. The ALB inspects the host header and path to choose which target group handles this request. Welcome to the virtual private cloud, the VPC. Think of it as a private, walled campus inside AWS. The first gateway is the Internet Gateway, the IGW, the door between the VPC and the public Internet. Without it, nothing from outside can reach in. Inside the VPC, there are subnets, neighborhoods. Public subnets route to the IGW. Private subnets do not. The ALB lives in the public subnet, facing the street. EC2 instances, they live in the private subnet, the back office, not directly exposed. How does traffic know where to go? Route tables, GPS routing rules for the VPC. The public table says, default traffic goes to the IGW. The private table might route through a NAT gateway. Now security. Requests pass through two checkpoints. The NACL, a stateless filter at the subnet boundary, and the security group, a stateful guard at the instance level. If the guard lets a request in, it automatically allows the response out. The ALB selects a healthy EC2 from its target group and forwards the request to 10.0.2.47 on port 8080. The packet has finally reached the application. The web server, maybe Jinx or an Express app, receives the HTTP request on port 8080. The application framework matches the path, / to a route handler. Does the app have everything it needs right there? Maybe not. It might query a database, say RDS Postgres at 10.0.3.12, or call an external API for dynamic content. The app builds the response. It sets headers, content type text / HTML, cache control max age 3600 to tell CloudFront and the browser to cache for an hour. It might set a cookie for session management. It compresses the body with gzip or Brotli. Status code, 200 OK. The response is ready to travel back. The response travels back through every layer, in reverse. EC2 sends it to the ELB. The security group allows it out, stateful, remember? Out through the IGW, back across the internet. At the CloudFront edge, the response gets cached, so the next visitor gets it instantly. Then through the ISP, your router, Wi-Fi, into your laptop, up the OS stack, and into the browser. TLS decrypts the bytes. TCP confirms delivery. The browser holds the raw response, status code, headers, and HTML body. The connection stays alive for reuse. Think of this as assembling, painting, and showing the page on stage. The browser runs a precise pipeline. Step 1. Parse HTML into a DOM tree, a structured representation of every element. Step 2. Parse CSS into the CSS SWAM, the style rules tree. Step 3. Merge them into the render tree. Only visible elements with computed styles. What about JavaScript? If the parser hits a script tag without async or defer, it pauses, downloads, executes, then continues. Meanwhile, the browser fetches sub-resources in parallel: images, fonts, style sheets. Step 4. Layout. Calculate position and size of every element. Step 5. Paint. Fill in pixels, colors, text, borders. Step 6. Composite. Layer everything and send to the GPU. Content appears on screen in about 300 to 800 milliseconds. When you type a URL and press enter, the browser makes a direct navigation, no restrictions. But when JavaScript on DevXOps.tech tries to fetch data from a different origin, the browser's passport control kicks in. That's CORS, cross-origin resource sharing. For simple requests, the browser sends it and checks the response headers. For anything more complex, the browser sends a preflight request first, an options request asking permission before sending the real package. CORS is enforced by the browser, not the server. Here's the full journey. You typed a URL. The browser checked caches. DNS resolved the host name through recursive resolvers to Route 53. The OS built a packet, sent it through Wi-Fi, ISP, to the CDN edge. TCP and TLS secured the connection. CloudFront checked its cache, forwarded to the ALB. The VPC routed through subnets and security groups to EC2. The app built a response that traveled back. The browser parsed, rendered.